The vastness of space has always captivated us, and how do we experience this final frontier most often? Through the lens of Hollywood, of course. But how much of it do they tell us correctly? Space operas and sci-fi thrillers often take creative liberties. In this video we will embark on a cosmic journey, separating fact from fiction. Get ready for a cosmic reality check. Space battles and explosions look amazing, don't they? The deafening roar of engines, the shattering boom of lasers, it's an auditory spectacle. But here's the catch. In reality, space is eerily silent. In the vacuum of space, there's virtually nothing for sound waves to travel through. Those spectacular explosions that we see in the movies? In reality, they would be completely silent. A supernova, the most powerful explosion in the universe, would be a silent spectacle. Without the distraction of sound, the visual splendor of nebulae, galaxies, and distant planets takes center stage. So, while the movies may thrill us with their sonic booms, remember the truth: space is a silent symphony. Picture this. An astronaut, caught in a perilous situation, loses their spacesuit. What happens next? Instantaneous freezing, right? Not quite. While it's true that space is incredibly cold, the process of freezing in space is a bit more complicated. In the vacuum of space, with no air to conduct heat away, the primary way your body would lose heat is through radiation. And radiation is a relatively slow process. So while exposure to the vacuum of space is undoubtedly fatal, it's not because you'd instantly freeze solid. You'd actually have a few agonizing minutes before losing consciousness due to lack of oxygen. Your body would slowly begin to cool down, but freezing would be gradual. The more we know about the real dangers, the better equipped we are to explore it safely and responsibly. Let's address another dramatic yet inaccurate portrayal of space's dangers, the infamous exploding astronaut. You know the scene? Someone's spacesuit gets punctured, their eyes bulge, and then, boom! Our bodies are actually quite resilient, even when exposed to the vacuum of space. Yes, the lack of atmospheric pressure would cause some swelling, but we wouldn't burst like overinflated balloons. Our skin, muscles, and bones are strong enough to hold us together. The real danger in space is the lack of oxygen. You'd likely lose consciousness within 15 seconds, and brain damage would follow soon after. So, while venturing out into space without a spacesuit is a recipe for a very bad day, it won't turn you into a human firework. The asteroid field. A staple of science fiction, these cosmic obstacle courses test the mettle of even the most skilled pilots. We see spaceships dodging and weaving through a dense maze of space rocks. But are asteroid fields really the treacherous gauntlets that movies make them out to be? Not really. While it's true that asteroid fields contain a lot of debris, the distances between these objects are vast. Even in a seemingly crowded asteroid field, the average distance between asteroids is estimated to be hundreds of thousands of miles. So, while asteroid fields are certainly something to be aware of, they wouldn't require the death-defying maneuvers we often see on screen. The Hollywood depiction of asteroid fields as chaotic, jumbled mazes is more fiction than fact. Few objects in the universe inspire as much fear and fascination as black holes. These enigmatic entities have captured the imagination of scientists and the public alike for decades. Movies often depict black holes as cosmic vacuum cleaners, indiscriminately sucking up everything in their vicinity. This portrayal, while dramatic, is far from accurate. But this is a gross oversimplification of how black holes actually work. In reality, black holes are much more complex and fascinating. While it's true that black holes exert an incredibly strong gravitational pull, this force weakens with distance. The gravitational influence of a black hole diminishes as you move further away from it. If you were to replace the sun with a black hole of equal mass, Earth wouldn't be sucked in. The gravitational pull would remain the same. It would continue to orbit the black hole just as it orbits the sun now. The orbits of the planets would remain largely unchanged. The real danger zone is the event horizon, the point of no return. This is where the gravitational pull becomes inescapable. Once you cross that threshold, gravity becomes so strong that nothing, not even light, can escape. This is why black holes appear black. They trap all light. So, while black holes are certainly powerful objects, they're not the cosmic monsters that Hollywood often portrays them to be. They are fascinating and complex phenomena that continue to intrigue scientists and challenge our understanding of the universe. In the heat of a space battle, we see spaceships making impossibly tight turns, dodging enemy fire with the nimbleness of a fighter jet. But here's the thing, space doesn't have air resistance. Once a spacecraft is in motion, it will continue in that direction and at that speed, unless acted upon by an external force. This means that stopping or turning in space requires careful planning and the use of thrusters. To slow down, a spacecraft needs to fire its engines in the opposite direction of travel. To turn, it needs to fire thrusters to create a rotational force. These maneuvers take time and consume fuel, which is a precious commodity in space. So while we may marvel at the on-screen agility of fictional spacecraft, the reality of space travel is a bit more deliberate. From the menacing creatures of Alien to the adorable E.T., Hollywood has presented us with a wide array of extraterrestrial life forms. But one common thread runs through many of these depictions. Aliens often look remarkably, well, human. 2 arms, 2 legs, a head with eyes and a mouth, it's a familiar blueprint. But is this anthropocentric view of alien life justified? Not necessarily. On a different planet with a different atmosphere, gravity, and chemical composition, life could take on wildly different forms. Imagine creatures that thrive in the crushing pressure of a gas giant's atmosphere, or silicon-based life forms that inhabit scorching hot volcanic vents. The possibilities are truly endless, limited only by our imagination. So, while it's fun to speculate about humanoid aliens, it's important to remember that the universe is full of surprises. Beam me up, Scotty. Teleportation, the ability to instantly transport oneself from one location to another, is a staple of science fiction. From Star Trek to countless other sci-fi universes, the concept has captured our imaginations for decades. But is there any scientific basis for this fantastical technology? Can we ever hope to achieve such a feat in reality? The answer, unfortunately, is not really. The challenges are immense and currently insurmountable. Teleportation, as depicted in movies, involves disassembling a person at the molecular level, transmitting their information, and then reassembling them at the destination. This process is far more complex than it appears on screen. The problem lies in the sheer amount of information stored within a living being. The human body is composed of trillions of cells, each containing vast amounts of data. Every atom, every molecule, every single component of our physical form, every neuron connection would need to be perfectly recorded, transmitted, and reconstructed. The brain alone, with its billions of neurons, presents a monumental challenge. The slightest error could have catastrophic consequences. Imagine a single misplaced atom in a critical part of the brain. While true teleportation remains firmly in the realm of science fiction, there have been some intriguing developments in the field of quantum teleportation. This involves the transfer of quantum states rather than physical matter. Scientists have successfully teleported the quantum states of photons, which are particles of light. This is a significant achievement in the world of quantum physics. But teleporting a complex macroscopic object, such as a human being, involves challenges that are exponentially greater. Let alone a human being is still light years away. The dream of teleportation may inspire us, but for now, it remains a distant possibility, a tantalizing glimpse into a future that may never come. Time is a funny thing, especially in the vast expanse of space. It doesn't behave the way we are used to on Earth. Movies love to play with our perception of time, depicting astronauts returning from space missions to find that years have passed on Earth, while they've only aged a few days. These dramatic portrayals capture our imagination and make us wonder about the true nature of time. While it's true that time can behave differently in strong gravitational fields, the extreme time dilation we see in movies is often exaggerated for dramatic effect. In reality, the effects are much more subtle and require precise conditions to be noticeable. Einstein's theory of general relativity tells us that time is relative, and it can be affected by gravity and motion. This means that time can speed up or slow down depending on where you are and how fast you're moving. The closer you are to a massive object like a black hole, the slower time runs relative to an observer farther away. This phenomenon is known as gravitational time dilation, and is one of the fascinating predictions of general relativity. However, the time differences we experience in everyday life, even with astronauts on the International Space Station, are minuscule. The effects are so small that they are barely noticeable without precise instruments. Astronauts on the ISS age about 5 thousandths of a second slower per year than people on Earth. a difference that's negligible for all practical purposes. This tiny discrepancy is due to the combined effects of their speed and the weaker gravitational field at their altitude. To experience significant time dilation, you would need to be in a very strong gravitational field or traveling at a significant fraction of the speed of light. Such conditions are far beyond our current technological capabilities, but they offer a glimpse into the strange and wonderful nature of our universe. Exploring space has always been an exciting adventure. From epic space battles to encounters with alien life, movies have fueled our imaginations and ignited our curiosity about the cosmos. But as we've seen, Hollywood doesn't always get it right. The truth is, space is even more mind-boggling and awe-inspiring than what we see on the silver screen. So, the next time you're watching a space movie, take a moment to appreciate the creative license and the suspension of disbelief.